Okay, we're in section 101. As always, there'll be contents. This will be a tough read. There'll be examples to look at and then exercises to do. All right, my name is Ron Bannon. This is a draft version of my adaptation of Webster Wells' Advanced Course in Algebra, which dates back to 1904. This PDF document is being made available to the Prison Mathematics Project participants only. I do realize that there may be teachers and students watching these videos, and they might be interested in getting a copy of this document. It has not been published, but it will be published at a later date. If you're interested, you can reach out to me. My email address is Bannon, that's B as in boy, the @ symbol, NNON.US. All right, let me go through the reading. Again, we're trying to encourage you to read this stuff over here, and certainly as you're reading through that, they say exponential and logarithmic functions. All right, so I'm going to just kind of, certainly, the binomial theorem, that's something you've seen before. All right, generalized binomial theorem. They kind of extend it. I know it's difficult to read through this stuff over here. I'm going to kind of point out some important things, though. This is really important. That's a series for e to the x. That is true for all x. All right? They talk about what happens if you have a different power, like mx, you just plug it in. Pretty simple to do. All right? They talk about if you have a different base. Pretty simple to do. They talk about, natural logarithms now. That's base e. Why is that? Well, if they've got this series over here, it's going to certainly relate to logs. All right? So what they do, and again, just paraphrasing what they're doing, they're expanding. All right? And you eventually get to something that might be kind of hard to follow. But they get to this over here. All right? So that's another really important series to come up with. All right? There's many ways to get that. I realize at this level of mathematics, so this might be a tough sell. The bottom line is I wouldn't worry about it. We're not asking you to memorize much. In fact, I'm not even asking you to memorize any of this stuff over here. I'm asking you to use it. Now, he does interesting things about this, and I want to point out the reason he does interesting things about this. He wants you to be able to evaluate logs using these series. And he goes through a bunch of problems and eventually comes up with something. Whoops, I got to go for a way to come up with that. Where was that? This thing over here. All right? Okay. Let's talk about the problem they gave you and what I would do. All right? So let it be required to calculate the Napier logarithm 2. What does that mean, log base 2? Let me write this down for you. So it's going to be the natural log of the number 2. What does it mean? Log base e of the number 2. All right? So, if you were looking at it, someone said, could you approximate that number? What I'm going to do is, look for easy things to do. So, log base e x to the y. And I'm going to, put down some numbers here and just talk about what x would be. So let's say y were 0. What would that give you? E to the 0, which is 1. So x would be 1. All right? All right, let's do another one. Let's say y was 1. What would you get? You get x to be e. And I hope you realize that e is a number. It's 2 point something. So I'm going to say log base e of 2 is somewhere between 0, bring that over there, and 1. All right? Again, why is that? Well, it's that comparison we're doing. Now, that doesn't tell me what it is, but I'll be honest with you. I do not think I'd use a series to figure out what that number is, but I do know it's between 0 and 1. What I would do is I'd use a calculator. So I actually tell you that. I say I'm using a calculator. Now, if you use a calculator over here, you're going to get this number over here. On a calculator, the bottom line is you're going to see the natural log of 2. And you'll see that key on your calculator. Now, if you type this into a calculator, if you type in ln2, whoops, sorry about that. If you type in ln2 in a calculator, the calculator will be spit back to you ln2. So what you need to do is you need to do ln 2.0. And if you do that, the calculator is going to spit back an approximate. And it's going to spit that back. Now, when I say that back, They might have more digits, less digits. It depends on your calculator. All right. So I'm gonna erase that, and I'm gonna say you really should learn how to use a calculator. You really should do that. All right. But I want to talk about the series. Right, the series, and let me write it down for you. The series that we told you about. All right, it's over here. That log base e of m over n is equal to 2 times, this has a really nice pattern to it. Again, we're not asking you to memorize. We're asking you to look at it. I'm just writing this down for you. You know what? I wrote a wrong thing down. I just noticed it. Sorry about that. I had 2 on my mind. Let's take a look. And then it's going to be 1/5. I forgot to put the 3 there too. Sorry about that. M minus n, m plus n to the 5. And by the way, you know, I'm saying it's got a pattern to it. I mean, I'll put this 1/7. I could do this forever. I don't want to do it forever. I can say yada, yada, yada. So I want to write this down for you. What do they want to do? They want to do log base e of the number 2. I got to write it as a fraction now, so it's going to be log base e of 2 over 1. You could use different numbers, by the way, but I'm saying 2 over 1 is probably the easiest one. And I'm going to write this down now. All right, so what are you going to get? You're going to get 2. And I'm going to tell you the m in the problem is 2, right? I'll write that down for you. So the m is 2, and the n is 1. So every fraction, let me point out what I mean by that. Every fraction is going to be the same, right? So it's going to be m minus n. So I'll write this down for you. M minus n over m plus n. Well, that's going to be 2 minus 1, which is 1. And m plus n is going to be 3, right? So I don't need to compute that over and over again. I just write it down. So it's going to be 1/3 plus 1/3. I'm just using the formula. And again, the formula that we're using is this one over here. All right, 1/3. 1/3 cubed plus, let's see, 1/5, right? 1/3 to the 5th. And someone says, when is this going to stop? It never stops. All right, let me keep writing this down. So it's going to be what? 1/7 now. 1/3 to the 7 plus 1/9. 1/3 to the 9. And again, this goes on forever. It just doesn't stop. So what do you get next? 1/11. 1/3 to the 11. And then I'm going to say plus dot, 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 goes on forever. I'm going to write this down as a summation now. And let me see if I can do that. And, let's take it, if we can do that. 2, the sum. Well, I'm going to see if I can do that. And let me write this over here. That's to the first power, right? So I'm going to start, it's going to seem strange to me, but I'm looking at the power first. 1, 3, 5, 7, 9, 11. I think I can do that. And what I mean by that, this is not very clear. I'm going to make it more clear. I know there's 1/3 here, and it's to an odd power. So I'm going to put down, it's an even number plus 1. That'll make it odd, right? So where would I start with? And we'll check it out, by the way. N equals 0. And I want to see if I get those 1/3 to the power problem here. So if I took 0, you get 1/3 to the 1. I get this. That's true. What's the next one you're going to get? Well, if I took 1, you get 1/3 cubed. And 2 would be 1/3 to the 5th, so forth and so on. So I'm pretty comfortable with that part. Now, what I got to do is I got to do this thing in front of it, right? And I'm looking at it, and it looks like it's, the thing in front of it, and I'll point this out to you with a color. I'm seeing that, right? Now someone says, I don't see it over here. Well, I'm going to write it down for you now. I'm going to say it looks like 1 over 1. Right? 1 over 1 is 1, right? So, it's always 1 on top, and the bottom number is 1, 3, 7, 9, 11. That's odd. So I'll put this over here. So what does it look like? It looks like 1 over 2n plus 1. And I want to check that out too. So if I took 0, I get 1 over 1. If I took 1, I get 1 over 3. 2, I get 1 over 5. Yeah. And where's it going? Going off to infinity. All right. So I asked with you. Wells is big on, because he's before the digital computer. He's big on doing a computation. I'm going to use a calculator. And using a calculator here, again, you could do this on a calculator. And how far do you go out? As far as you like. And a calculator can do that pretty quickly. I want to point out that you can actually type this into Sage. I also want to point out in Sage you could end this at a finite number. And you may want to play with it. Like make it 1,000, make it 10,000. All right? You can do whatever you want. All right? Do it. I really do mean that. Play around with it. But here's the deal. I think for the most part, I don't think I want to do a series expansion to find out the log base e of 2. I would just use a calculator, and I really do mean that. So I want to just, briefly talk about what I'm talking about over here, that I think it's important to read through the section. It's a great introduction, all right? When you take calculus, you'll be seeing this more and more. But I'm going to say when you're doing the exercises, I'm going to say you may want to just play around with the series for both the natural log and for a. But I got to be honest with you, I would be basically just using a calculator, all right? So it says use a table. I wouldn't use a table, by the way. Now someone says, why does Wells say use a table? That's what they had back then. They didn't have a digital computer, all right? But it says, find the Napier logarithm. That means base e, and they say significant figures. Wow, each of the following to 4 significant figures. Well, I got to do that, right? All right, of the number 1,000. Wow. So what do you do on a calculator? It would be the natural log of 1,000. I want to repeat, if you did this on a calculator, you're going to find out the calculator will spit back to you natural log of 1,000. Now, it may simplify it. I'm not saying it wouldn't simplify it. It may, write down something a little bit different than that. I want to point out what it might write down. It might write down 3 natural log of 10. That's a possibility. By the way, that might be easier to approximate it if you did that. I'll tell you why. It's easier to place, that number, natural log of 10, between 2 and 3. All right? E squared and e cubed. All right? I can do that. But again, my claim over here is I just want to get the number. So what would you do? Natural log on a calculator, 1,000.0. And then you get an approximate number. And again, I'm hoping you're getting this number over here. All right? So this one over here, use table of common logarithms to find a Napier logarithm. By the way, I didn't read that part up here. I want to point out, I don't think I'd go there either, and I'll tell you why. If I'm using the common logarithms, I'd have to rewrite the problem. Maybe I should show you what that means, that your natural log of 2 is going to be the natural log, I'm sorry, not the natural log, I'm going to do base 10, right? It's going to be log base 10 of 2 over log base 10 of e. All right? But again, I don't think I want to go there. I just want to use my calculator. All right? But you could use the base change formula, which we've discussed in the past. All right, this one over here, again, if I were asked to do the natural log of that, and let me write down what I mean by that. The natural log of 0.0001. Again, if you're using a calculator, the calculator will have no problem with that, and you should get this number over here. All right? All these questions, by the way, I would be using a calculator. I wouldn't be using a series expansion. I would not be using a table. I wouldn't be using a base change formula. All right? So what do they want you to do? Compute logs. We give you the answers. Please look at the answers and make sure you know what those answers are. Okay? Again, logs, more logs. Let's keep on looking at that. Again, read through that. I know they're asking for a number of digits there. Yeah, some thinking's required. I know that. All right, and it's important to know that there's things given. I give an explanation in the wording of it, hopefully making some sense out of that. They were big on that back then, not so much anymore. But okay, then you get to Sage. I do want to point out. Whoops, sorry about that. In Sage, it's a computer algebra system. It's open source. Go to this website. You can download the application or use the interactive web-based application. I want to point out, though, in Sage, when you write down log in Sage, L-O-G, and you give it a number, it's actually base A. Now, the reason for that is in upper-level mathematics, log means base A. But in lower-level mathematics, log means base 10. That's confusing to some students. But what you can do with Sage is you can define any base you want. Any base you want. So, for example, over here, I'm saying base 5. Right? So this is log. I'll tell you what this means. This log 758 base 5, which means log base 5 of 758. All right? Now, if you just put log of a number like 2.0, this would mean natural log of 2.0. All right, keep that in mind. That's the base. And again, we give you some examples over here to look through. All right. We also give you an example of a summation. And I believe the summation we're giving you here, I'll write that down for you, is the one we originally talked about. And I'm summing this from 1 to 100. All right, from 1 to 100. And I know I wrote a different series down there. It's n minus 1, 2n minus 1. I wrote down 2n plus 1. And in that case, I'd start with 0. This one, they're starting with 1 because that would give you 1 to start with. But you get the number. All right? So you may want to play around with Sage. My goal here is not so much to get you to play with Sage, but just to work Wells's problems and try to understand what these give you. If you have any questions about my work, saying, oh, I think you made a mistake, please email me at my email address, which is Bannon, B as in boy, @NNON.US. What am I talking about? If you're in this section and you're working these problems and you believe I made an error, you would email me, tell me you're in 101.3, tell me you're working problem number 4, for example, and tell me you believe I made a mistake in the answer, and I'll look at it. I'll determine if I made a mistake or not. And again, if I'm confused, I'll write back to you. But for the most part, I'll make the correction, and I'll cite your name as being helpful in the creation of an improved document. And I will put your name down. Right, so please, if you do email me, please use your full name. If you do not want to be listed on the book, though, just tell me, please do not list my name. And I won't list it. All right, I'll honor that. All right. And also, if in the future, if you want your name removed from the document, what you do is say, remove my name from the document. Now, the problem with a PDF, though, is once a document goes out, people have copies of it, and I can't remove your name from copies. All right. So I can only remove the name from future copies of the document. All right? Okay, so that's it. Thanks for paying attention, and I hope that was helpful. Good luck to you.